So now we will take up a complete problem for analysis. I'm going to take, um, before I write the function module, talk about selection sort. All of you know what selection sort is. You've already done it in your CS110 course, 1100 course, and we will see how to analyze this program completely. And as you know, selection sort, what it does is it divides the array into two parts, one which is the sorted portion and another which is the unsorted portion. Let's say I have something like this. And just for convenience, we will assume that indices go from 1 to 8. A of 1, A of 8. So what does it do initially? This is the sorted portion of the array. And it's written as A of 1 to I. We assume that this is already sorted. And this corresponds to the unsorted portion of the array. Okay. Now let us look at the analysis of this. And so what does it do next? It takes this as the starting point, pointer I here, and another pointer J here. And that elements and J goes from, let's say, this is the minimum value. This is assumed to be the minimum value. Minimum is equal to A of 1. And it compares all the elements from 2 to 7 with the minimum value, finds the location of the minimum value, and exchanges the two of them. So after one pass through the array, that means what? I have looked at 7 elements in this case. I have made 7 comparisons in the array, and I get 1 here, 2, 3, 8, 4, 6, 7, and 5. So now what can we infer after this, or what can we assert after this? This portion of the array is completely sorted, and this is the unsorted portion. Okay. Now next what we will do is, so clearly sorted portion is already sorted, and we also know that all the elements in the sorted portion of the array are smaller than the elements in the unsorted portion of the array. So then what do you do? We start with the unsorted portion. Again, start with, you're only going to sort this part. And you start with the element 2. And again, assume it to be the minimum. Five. Then you find out, it turns out that this is the smallest element, and you exchange it with itself, and then you augment the sorted portion of the array to include 2 elements. So you keep repeating this until you come to n-1, which is compared to the last element, and you're done. So every pass through the array augments the sorted portion of the array by 1 element, and repeats this until all the elements are exhausted. But notice that during every pass through the array, for example, when I started with the first element, I've compared with 7 elements. When I started with the second element in the array, I've compared with 6 elements. Then when I start with the third element, I start comparing with 5 elements, and so on. Okay. So let's see how we can use the rules to analyze the complexity of this program. Selection sort. Let me write the entire function now. Let's say I have as an argument int star a, which is an array a, and int n, which gives you the size of the array. Okay. And I have int I comma j. I keeps the pointer to the sorted portion, and this keeps the pointer, starting pointer for the unsorted portion. Okay. Okay. And P, let us say, is the location of the smallest element that we have found during that pass. Okay. So initially, what can we assert? We can assert that n is greater than 0 and I equal to 0. And the loop invariant will be a of 1 to I and is sorted, and all of a of 1 to I is smaller than all of a of I plus 1 to n. Since there's no element that exists for I equal to 0, this will be true, will imply this. When we write the loop over here for I going from 1 to n minus 1, right? Because I don't have to go to the end of the array. I assert. Now I corresponds to the j corresponds. What is j? J is the index to the unsorted portion. Okay, of the array. Remember this. What can we claim now? We can claim that 1 less than or equal to I less than or equal to n minus 1. This we can claim. Then we assign min to a of I and p to I. Now, what we're going to do is, assuming this j is the index to the unsorted portion of the array, in a for loop it's a bit difficult because we don't initialize these variables. For j equals I plus 1 to n, do if a of j less than min, then min is assign the value of a of j and p is assign the value of j, and if and for, and a of p is assigned a of I and a of I is assigned the value of min, and for, the main for block completes, end module. Okay. The loop invariant that I'm going to write here is a bit not so nice, but because I don't have the initialization for j, but assuming that j takes values for the unsorted portion of the array, we can assert here min is less than or equal to all of a of 1 to j, initially j is 0, and I is less than or equal to n minus 1. And we also have and I less than or equal to j less than or equal to n, and I less than or equal to P less than or equal to J, and min equals A of P. So this is a long loop invariant, which should become true as soon as you enter the loop. It's not true for the for block just outside. If you had written a while block, I could have initialized the value of J to I plus 1. Okay. Now, what we'll do is, now at the end of this for, what can we assert here? We can say that min is less than or equal to A of I to N. This is a nice assertion that we have. And min equals A of P. We can assert this over here. Okay. And finally, what can we assert here? A of 1 to N is sorted. Just to give you an idea of how we, these things are generally put in comments so that you know what you're actually trying to do. Okay. Now, let us try and analyze this algorithm. So for the analysis of selection sort, I need a few things. So what are the dominant computations over here? This comparison is there. And this exchange, this counting, locating the minimum is there. And when we are updating the min value and number of exchanges. Okay. So analysis of selection sort can involve, if you want to analyze it, look at the number of comparisons, number of exchanges, and number of updates of min. Okay. Now, number of exchanges is n minus 1. Why is it n minus 1? This statement is always, this set of statements are always executed. Okay. And so number of exchanges always happens, which is n minus 1. Number of times min is updated is a question mark because it depends upon the data that we have for sorting. So we'll ignore it for the time being. For now. Okay. Number of comparisons. This is easy to compute. As we already saw, during the first pass of the array, if you look at it, there's n minus 1, n minus 2, plus up to 1 comparison. So the total sum is n into n minus 1 over 2. Okay. So what is this now? That means number of comparisons is the dominant computation in the selection sort algorithm, and therefore we say T of n is equal to n into n minus 1 over 2, which is equal to big O of n squared. It can actually be shown to be theta of n squared. So what is the meaning of this? It says if the size of the input is n, it takes n squared computations. Okay. So grows as a square. It's a polynomial time algorithm, quadratic, sorry, computations to solve the selection sorter. That's what it says. So now let's go back to the program and do in terms of our order iteration. What do we see here? Let's look at the innermost loop here. So what do we have? This is like, this is, let's say, a program. Let me call this here P1. And within this program, there is a part which is executed here. This is P2. I have P1 and this is P2, and P2 consists of, again, a P21 and a P22, right? P21 and P22, and P22 again consists of segments of this kind. So you can keep subdividing a program into either compositions where P1 follows P2. And notice that what are we doing here? In this is P1 here. Within this, the P2, for example, has two parts, P21 and P22, run in sequence. So I'll apply the sum rule here. For P1, P2 runs P1 times, therefore I'll use the product rule. Here I have P2, and this again has, let me call it, it's a for block here. So it has here, P22 has P221 and a P222. That is the for block and the content in the for block. So let's look at this. This is going to be order 1, the comparison and the assignment. And this is going to be order n because it's done n times. And this is going to be order 1. And yeah, and this is order n. And this whole thing is order 1. So notice that the dominant computation, if you look at it, if I look at this part of the program, within this, for example, order n into order 1. So this for block, inner for block is order n into 1. And this one, for example, because that's the dominant computation here. So you have a small segment over here, these two, sorry, P of I and this. And if you look at it, there is a for loop which is costing you order n, and there is a for loop which costs us order n, and a set of assignment statements which cost order 1. So you have to apply the sum rule, and then you get that for the entire inner block, it's going to cost you order n, and this for loop is run order n times. Therefore, the analysis of, you apply the product rule and you get order n star n, order of n squared. Okay, so this is the time complexity of the selection stop sort algorithm. And yeah, maybe I will stop here. I want to talk about one more type of problem which you have already studied. And this is the, all of you know about binary search. And binary search, what does binary search do? It assumes that an array is sorted. Let's say I have elements like this, 2, 6, 10, 15, 25, 28, 31, and 34. And you want to search whether a particular key is present in the array or not. So what do? We define a middle element, and let's say again here, this goes from 1 to 8. So we say mid is assigned the value of 1 plus n by 1 plus 8 by 2, and we do integer division. So this is 4 here. So 1, 2, 3, 4. We compare with 4 here. So during the first pass, let's say the key that I want to check for is 0. So the first time what I do, I compare with this middle element, and I check whether it's smaller than the middle element or greater than the middle element, greater than or equal to. And I realize that 0 is less than 15. So I check in this portion of the array. So now I reduce the size of the array to 1 to 4 because I know very well it's not, because it's sorted, it's not going to be there over here. Then what do? I again divide the array into 2 parts. So I'll compare with the second element here, 2 and 6. It's smaller than 6. Then I divide it into 2 parts again. So I have 2 and 6 here. And I notice it's smaller than 6. Then once again, I divide it into, it's smaller than 2, therefore it has to be in this portion of the array. But I've already reached the end of the array and the key is not found. So if you look at it, I had 8 elements here. So the first comparison we did here, 1. Then we did one more comparison here, a third comparison, and a fourth comparison to get to the key. So you can very easily show that the binary search algorithm has a complexity of the order of log n. So, sorting makes a lot of difference. On the other hand, suppose I had an unsorted array. How long will it take? It could take linear in the number of elements. What do we mean by linear in the number of elements? I would have to compare with every element in the array to check if the array was not sorted. That is, if I had the same array, but the elements were in random order, I would have to check A1 to AN, and the time complexity could be as bad as order n. Most importantly, we always look at, I forgot to mention this, worst case time complexity. Okay. This need not always be the best complexity algorithm, as you will see in your algorithms course when you do what is called amortized analysis. And we are saying in the worst case, it can go through the entire array. It's possible that the first element itself was the key when you had even in random order, but we always look at the worst case complexity in terms of complexity analysis. And this kind of